Greetings. Welcome to the 12th lesson in a series of lessons on basics of power systems engineering. This lesson is on phasor representation of AC voltages and currents. Instantaneous values of voltages and currents are represented by sine or cosine time functions shown here on this page. I discussed these functions in a previous lesson. I'll go over them briefly here. V of t, the time function representing a voltage, is written as a maximum voltage Vmax times sine or cosine of omega t plus delta. Omega, which is the angular frequency, is written out as 2 pi times f, the frequency. F is the ordinary frequency, which is 60 Hertz for American system. And delta is the phase angle, written either in degrees or radians, as long as we keep track of the unit we have used. The same argument goes for the current equation. It's good to know the time function and its structure for voltages and currents. However, in studying AC circuits, we almost never use these equations directly. Instead, we use something called a phasor representation of these. Since the frequency f is a constant, it means that omega, which is 2 pi times f, is also a constant. So all we need in order to uniquely identify this equation is the Vmax and the delta. The rest is already known. Of course, when we are given a voltage, we're given the effective value, but we can find the we can find the maximum value by taking the effective value, Vrms, and multiplying it by square root of 2. So that's not a problem. So all that's needed to uniquely identify a voltage or a current time function is the effective value and the phase angle. As an example, if I'm told that the RMS value of a voltage is 120 volts and its phase angle is 30 degrees, I can first calculate Vmax. So V, the effective value or RMS value, equals 120 in our example case, and delta equals 30 degrees. I can calculate Vmax as square root of 2 times 120, which comes to 169.7 volts. And knowing that, I can write V of t equals 169.7 times cosine of 377t plus 30 degrees. 377 comes from multiplying frequency by 2 pi. So it's 2 pi times 60 comes to 377, and the unit is radians per second. The magnitude and phase angle, the magnitude of the voltage or current and the phase angle form a duo, and that duo is called the phasor representation of the voltage or current. You can see them right. So you can see the phasor representation of the voltage here. Usually a phasor quantity is written out in bold typeface, while the scalar quantity is written as an ordinary letter without making it into bold. Delta can be in degrees or radians, as long as we keep track of its unit. Same argument, of course, goes with for the current, with its phasor form shown in here. I in phasor form equals I as a quantity, effective value of the current, with an angle beta. I'll continue the lesson focusing on the voltage phasor, and the treatment of the current phasor follows a similar path. A convenient way of representing a phasor is as a magnitude and angle on a Cartesian plane, seen here. So this phasor is represented by a line segment, a directed line segment with a length of v, this v here, that forms an angle of delta with the horizontal axis. We will now convert this Cartesian plane into a complex plane by having the horizontal axis representing the real quantities and the vertical axis representing the imaginary quantities, as shown here. This will enable us to introduce a second way of representing the phasor quantity v as a complex number with a real and imaginary part. The real part is the horizontal component of the phasor, which equals v times cosine of delta, this line segment here. And the imaginary part of this complex representation would be the vertical component of this phasor here, which would be v times sine of delta. Here is the complex form of the phasor. V equals v cosine of delta, this component, the real component, plus j times v sine of delta, which is the vertical component or the imaginary component. There is yet another way of representing any phasors, and that is called the exponential form. It takes advantage of an identity called Euler's identity. Let me write that out. In general, Euler's identity says e to the power of j theta, j times any angle in radians, equals cosine of that angle plus j sine of that angle. Of course, j is the purely imaginary number, square root of -1. Having this identity, which converts an exponential form into a Cartesian or complex form, we can convert this equation into its equivalent exponential form. So let me starting with this v, the phasor of the voltage, equals v cosine delta plus j v sine delta. I take the v out, this scalar v here, out as a factor and end up with cosine of delta plus j sine of delta in pair of parentheses here. And based on Euler's equation, I can rewrite this as v e to the power of j delta. So this is the third form of representation of this phasor representing this time function. The magnitude angle form, the complex or rectangular, sometimes called Cartesian form, and the exponential form here. At any given moment, one or the others of the three forms may be the most convenient form to use. I'll take a quick detour here to introduce myself, and we'll follow it by working out an example to practice with the phasors. My name is Fuad Alvandi. I am a PE in electrical power engineering and licensed in the state of Maryland. This is the 12th lesson in the series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name and web address and email address on this page. You can visit my website where you'll find comprehensive modules on topics in power systems engineering. My website is own-your-destiny.mylearnworlds.com. If you're looking for a resource to review topics in preparation to take the PE exam, in electrical power engineering, you'll find the modules on my website to be helpful. I will now continue this lesson with an example. We're given a voltage and a current, each as a time function here, and asked to write their equivalent phasor in all of its three forms. Calculation of power factor and power factor angle are also asked for. We know that to form the phasor form of these equations requires knowing the voltage and current as their maximum values. Well, excuse me, as their RMS values. The maximum values are shown here. From these two quantities, the Vmax and Imax, we can find the effective value of the voltage and current. So the first step is to divide each of these by square root of 2 to get the RMS value of V and RMS value of I, which I typically show with just V and I. Here are those values. V RMS, or effective value of V, equals this quantity over square root of 2, that comes to 240 volts, and I RMS equals this quantity, I max, over square root of 2, that gives us 10 amps for that value. The angles for each of these two are immediately known by just looking at the equations. 40 degrees for voltage and 25 degrees for the current. So the magnitude angle is immediately known. Magnitude angle form of the phasor for these are known by having the effective values and the phase angles, and it's written here for voltage, 240 with 40 degrees angle and 10 amps with 25 degrees angle. Now let's convert these into their Cartesian or rectangular form. V in Cartesian form is V times cosine of 40 plus J V times sine of 40. V being the effective value of 240. And the answer is 183.9 plus J 154.3, all these values in volts. And similarly for the current phasor, we have 10 times cosine of 25 in this case, plus J10 times sine of 25. And this is the Cartesian form of the current phasor, 9.063 amps plus J 4.226 amps. And the exponential forms are seen on the next slide. And they're simply effective value times e to the power of j times the phase angle. 240 e to the power of j 40 degrees for the voltage, and 10 times e to the power of j 25 degrees for the current. Power factor angle is simply the difference between the 40 and the 25, and that comes to 15 degrees. And the power factor itself is found by taking the cosine of this angle. So the power factor, sometimes shown, very often actually shown as PF, equals cosine of 15 degrees, which is 0.966 and lagging. This is sometimes written as 96.6% if you multiply it by 100. Lagging because the current lags the voltage. If you look at the angle for the current, it's less than the angle for the voltage, so the current lags the voltage, and that's how we characterize the power factor, lagging in this case. We are at the end of lesson 12. This is Fuad Albandi, founder and instructor of the educational group Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button and the notification bell. Thank you for watching this video, and I hope to see you in another one of my presentations.